Welcome to video 5 of our chemistry series. Today we'll explore VSEPR theory and hybridization, which explains how atoms form different molecular shapes. First, what is VSEPR theory? VSEPR stands for valence shell electron pair repulsion. This theory helps us predict the 3D shapes of different molecules. It's based on one simple idea. Electron pairs will repel each other because they have the same negative charge. To minimize this repulsion, electron pairs are spread out as far as possible around a central atom in a 3D space, resulting in a 3D geometry. One key concept to understand is electron domains. An electron domain is any area where electrons are located around the central atom. This includes the bonding pairs, which are the shared electrons that form bonds, and lone pairs, which are the non-binding electrons. There are two different forms of 3D geometry, electron and molecular geometry. Electron geometry, also known as electron domain geometry, considers only electron domains. However, molecular geometry considers electron domains as well as the amount of lone pairs around the central atom. Let's look at this on the VSEPR table. So this is the VSEPR table, or the VSEPR chart. This shows the relationship between the number of electron domains and the number of lone pairs in a molecule and its resultant 3D geometry. As you can see here, a molecule with 3 electron domains and 1 lone pair will result in an angular or bent geometry, and a molecule with 5 electron domains and 3 lone pairs will result in a linear geometry. Let's look at an example here, H2O, water. The electron geometry for water is tetrahedral because there are 4 electron domains, 2 bonds, and 2 lone pairs. However, its molecular geometry is bent because the molecular geometries are taken into account. The lone pairs are taken into account in molecular geometry. So here you would have 4 electron domains, but as 2 lone pairs as well, resulting in an angular or bent molecular geometry. Now let's take a look at electron geometries. So here are the main 5 electron geometries that are on the VSEPR table: linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Now let's look at bond angles. Let's talk about bond angles. Bond angles are just the angles between the atoms relative to the central atom in a 3D space. So linear molecules have a bond angle of 180 degrees, which is this right here and over here. Trigonal planar molecules have bond angles of 120 degrees, here, here, and here. Tetrahedral bond angles are very specific, at 109.5 degrees. Trigonal bipyramidal bond angles are both 90 degrees and 120 degrees. And octahedral bond angles are all 90 degrees. There are specific bond angles for these molecular geometries as well. However, it is important to note that you do not necessarily need to memorize these, especially in lower level chemistry. Just note that all of these bond angles are going to be smaller than these electron bond angles, and that is due to lone pairs. Lone pairs take up more space than bonding pairs in a 3D space, causing bond angles to reduce and shrink, because these lone pairs cause a stronger repulsive force which pushes atoms closer to each other, thus reducing their bond angles. Now let's talk about hybridization, another very important concept in VSEPR theory. To explain molecular shapes more fully, we need to understand hybridization. This is the process where atomic orbitals will mix to form new hybrid orbitals that will align correctly and are better suited for 3D geometry. As you can see in this image, we have an s orbital and a p orbital split into a y, x, and z axis. These orbitals will combine to form an sp orbital. This hybrid orbital is better suited for a 3D geometry. So the main types of hybridization are sp, sp2, sp3, sp3d, and sp3d2 hybridization. Each of these hybridizations align with certain rows and columns on the VSEPR table. sp hybridization aligns with all geometries with 2 electron domains. sp2 hybridization is 3 electron domains, sp3 is 4, sp3d is 5, and sp3d2 is 6. To learn more about the in-depth concept of hybridization and pi bonds and sigma bonds, please look for further videos. So now let's look at examples using VSEPR theory. First, let's start with methane, CH4. So if you draw out the Lewis structure for methane, as we learned in our last video, you'll see that methane has four electron domains. Has 4 bonds, 4 electron domains, but 0 lone pairs. So if you follow the VSEPR table with this knowledge, you'll see that methane has a tetrahedral 3D shape, which results in 109.5 degree bond angles. Here's the 3D shape for tetrahedral. It is also very important to note that when drawing Lewis structures, you also want to take into account the 3D shape of a molecule to get a more detailed Lewis structure, which is why this CH4 is more detailed as it shows the shape of tetrahedral. From a topside view, we have 4 H's spread out evenly, just as 4 H's are spread out evenly here. Another example is water, H2O. As we said before, H2O has 4 electron domains and 2 lone pairs, which results in it being a bent geometry. And as you can see here, this is shown in its Lewis structure. Now let's talk about polarity and molecular shape. Molecular shape affects polarity, which influences properties like boiling points and solubility. Polarity causes an uneven distribution in a 3D shape. Polar molecules, like water, are asymmetrical. As you can see here, you have partial positives on these hydrogen atoms and a partial negative on this oxygen atom. This creates an asymmetrical 3D shape as these bonds are getting pulled more towards this oxygen as it's pulling electrons more towards it. However, nonpolar molecules, like carbon dioxide, are symmetrical in their 3D shape. So let's recap. VSEPR theory explains molecular shapes by minimizing electron repulsion and helps us predict 3-dimensional shapes of various molecules. Lone pairs work to reduce bond angles in 3D shapes. Polarity impacts the 3D geometry of a molecule, specifically whether it's symmetrical or asymmetrical. And hybridization explains how atomic orbitals will mix to create bonds and create better orbitals that are more suited for 3D geometry and bonding. Thank you, and I hope to see you in the next video.